What's up, guys? So today we're going to be exploring these subjects here, and it's all kind of hierarchically under computation, where computation is just going to be defined as the controlled evolution of physical information bearing states. Um, that would obviously be in some kind of machine, if you will, under fixed operators acting on finite memory geometries. This is kind of like a not very. I mean, it's terse, but it's like there's a lot of things that have to be developed. And by the way, this is on my website, JetBundle GitHub.io. But yeah, so you can pause and read this if you want. But we're just gonna get right into it. Um, Also, just some notes. Um, there's really no single correct approach to self, education, or like andragogy, because there's like pedagogy and then there's andragogy. Pedagogy, like peda kid, um, not pedo. Sorry, but damn, I'm gonna get what's it called, banned off of YouTube. Holy shit. Anyways, andragogy. Um, Basically, I mean, I just say that really plainly because these notes should be read with a little bit of, I guess, humility, if you will. Like, I'm not like if you go on my website, it's not a curriculum, right? Like, there's no certification. There's really no claim of like completing anything either. Like, just in general, a philosophical approach. Sorry, I'm going on this tangent, but I think it's important because, like, you don't want to replace computer science, math, physics, or numerical analysis or anything with like what I'm about to do. It's a way to attempt and assemble a coherent picture of how just machines, um, information, how it gets transported in the air. With all, I mean, it seems like magic, like black magic, but I mean, it's physics. Memory, how numerical evolution in like scientific computing. So like researchers, scientists, engineers, all to some degree have some like self-directed learning that eventually becomes unavoidable, especially if you get into like research careers or like just engineering type careers. At some point you're going to begin assembling your own things, testing your own things, revising kind of a personal image of how everything works for to see just how all the pieces connect. So this is just kind of a way to have some philosophy with contact, if you will. um so you know when appropriate, the goal is just more of a unified picture of everything. All right. So most introductions to computing begin with software. um this I'm going to try just beginning with the machine itself. So by the way, again, you can just follow along and read, but the first question is not going to be like what is what is a programming language, right? We're not going to actually ask that. We're going to ask really what is a computer. Right, from a physical perspective, specifically, a computer is a finite, it's going to be a finite dimensional system, that is capable of storing and transforming information. So you can think about like memory, clocks, registers, communication channels. All of these things can be defined by like we can formalize this as a computing machine to be a state, basically just a microstate that evolves according to um, some transition map and some state set. Um, Now, what's kind of cool about this is a program then can be viewed as a special, a specification of this operator F, of just how you are choosing to, simply, the machine itself remains just the underlying physical object, but how, some initial data, then gets processed into some trajectory on the hardware. That is what a program is. Okay, but that's how we're going to formalize it. Um, and of course, what's kind of cool is the transition operator. This is a unit of execution. So you can think about cellular autonoma, or molecular dynamics, time steps, finite difference stencils. Basically, it's just state vector updated by a fixed rule. Okay, so that's usually what modern CPUs are concerned with. Okay, so we can visualize something, a cellular automation, which basically says observe a state, apply some update rule to that state, or some local rule. So specifically for rule 110, you would observe the next state and then apply the rule again, and then the CPU basically just does the same thing, but it does it on a much larger and more structured state space. But we just take this possible number of states that are available here, and then just kind of apply the next step, and you'll see patterns that only on a grid that you can see, and you can run it and fill out the fractal or whatever. But this would be like a nice cellular automation. Okay, and of course, I'll cover this a little bit more. But this would be like a nice computation for the entropy, defining microstates within the state space, or the cardinality of the state space is enumerating the microstates that are accessible. So, anyways, really, machines, what they do is they process information, right? So we have to ask, what is information? Before you discuss like memory or programming languages, it's probably worth asking, again, like it's probably worth defining information in terms of physical states in nature. So information is the distinguishability. It's the measure of distinguishability between possible states. So if a system can occupy W microstates, so just if it can occupy that many states, right, then you would define that the information required to specify one it occupies is log base 2 of W, right? So when the microstates are not equally likely, though, you can assign probabilities to each of those states that this state machine could possibly occupy. And so then the Shannon entropy would be classified as the probability multiplied by the logarithm of the probability. And so this just measures the average uncertainty before you actually measure it. So the Shannon entropy is, again, this is the Shannon entropy of the probability distribution, because entropy itself is a quantity that is defined in terms of distributions and probability distributions. Okay. Now these ideas, of course, memory stores information, computation will transform the information, communication will transport the information by copying correlated physical degrees of freedom across space. So, that's kind of nice. And much of computing then it will be viewed through these three verbs, just storage, transformation, and transporting. Or all of these verbs here correspond to memory, computation, and communication themselves. All right. So, you can also think of something like, and there's other, we can just kind of briefly go by compression. If you have a string such as like, sorry. It has low entropy per character because the next symbol is predictable. So a pseudo-random hex string here, per character maximum for its alphabet. And then compression would be the removal of redundancy. So Kolmogorov complexity as well. I kind of mentioned this slightly. This formalizes the shortest program that generates a string itself. So yeah, these are all just very nice, more really fundamental things about how machines work. Landauer's principle is interesting because it states that existing erasing in bits at temperature T dissipates at least this many joules of heat into the environment. So this kind of like I guess, a lower bound on how much heat gets generated by essentially, erasing a bit. So there's a thermodynamic cost, whether you're overwriting memory without retaining old value elsewhere. So also, I think there's in quantum computing there are some systems where you have a topological mode of compute where you're effectively generating zero entropy. So that's something to think about, or you could look that up. Just a cool fact. But yeah, Shannon entropy. The Shannon entropy, bits per character. You don't have to store anything because it's just all in one state, right? But because there's a bunch of different states here, you have to, you have to represent them in such a way that takes up a bit more entropy, right, and generates a bit. No, sorry. And then this is like if you have temperature here, and the minimum. This is like the equation, the lower bound for how much heat was actually dissipated when you erased a bit. And so it's like small. It's like in the 10 to the minus 19 joules, but I mean it's still there. So it's kind of a cool estimation. And it'd be fun to crank this out and calculate that, just for fun. But yeah, memory. So this is often where computation itself starts to feel really tangible when you have memory. Memory is not some abstract programming concept. Okay, it's actually a physical substrate that stores information. I mean, your brain probably, hopefully, if your brain is working right, you have memory, right? There is, the useful abstraction memory would be, if we wanted to define memory in such and formalize it, we'd say memory is a map where addresses, or the set from an address space, if we take some addresses, we map them onto a value space. So addresses map to values. That is memory. So for example, if you had 256 possible byte values, now the machine ultimately will manipulate addresses and values. And variable names will just be like conveniences for human beings. And the hardware itself is just going to tell you, like, it just knows, the hardware itself just knows locations and states, right? It just knows location and its own state. But, you have all of these objects that we're going to talk about, like pointers, bandwidth, physical degrees of freedom at the address held at P, latency, bandwidth, memory bounds. So, there are really, the machine ultimately, again, can only manipulate addresses and values, and the hardware itself only knows location within its own like space and the state of the machine itself. So a pointer is just a value that you can interpret as an address, and then the expression star p just means evaluate im of p, right? So we're evaluating from that address to a value for a read or update, for a write, or we're doing a pullback, right, from the im to this evaluation. And there's no indirection layer in the no magic indirection layer in the physics. So you only need a number stored in one cell that names another cell. So for example, I were to just instantiate x here as just writing it 5 into the cell named add x, right? Then what you do is store the address of x into the cell named p, and then you would write 10 into the cell whose address is stored in p. So after the final line, the variable name is not required for the update to occur. The machine changed the physical degree of freedom, right? Held in p, and I mentioned that earlier. But it's kind of nice because it allows you to pointers allow you to take advantage of this type of, update, um, where your map from the address space comes back uh, from the value space back into the address space. So it's just like a nice evaluation, if you will. So that's all a pointer is. Now, not all addresses are equally fast to reach. So again, the purpose really is not just to memorize or like just to learn what a pointer is. You have to think about the fact that computation um, is fundamentally a state transformation, right? It's a state transformation from memory. So that's the thing to mostly understand. And addresses themselves, you can get a bit into the more technical details, where you have registers that sit inside of a processor core. And L1 and L3 caches are small. SRAM banks, DRAM banks are large and slower. So you have an entire infrastructure within the system or within the state machine that, you have storage that's larger still and slower again. Each level of all of these things within the processor core trades latency. So time that it gets to attack the first byte against bandwidth or bytes per second that are sustained. So you have this kind of like hierarchy that is determined by this whatever equation, but a lower bound on the runtime. So you know that the runtime is going to be a lot. It's going to be at least the maximum of this, right? And that's how you would calculate this with the peak floating point throughout. Oh, sorry, throughput. Sorry, throughout. With the peak floating point throughput, and then when the second term dominates here, the program would be memory bound. Rearranging what you'd fetch matters more than shaving arithmetic. So this helps you make decisions. This is a nice physical constraint that is true no matter how whatever like your processor core has or however it's built. All right, now the memory map itself, again, say you have like an address, it's just here, this is your address, and then a value, and then your physical write at that address, and then you'd go through and store it, and you'd have a different address, but the pointer itself would give you the value. The value would then go back to the address, right? Or the value would take on the same, I guess like meta, like value as the initialized variable. All right, and then if you were to do, basically that's just kind of that's pretty much it. But this would take on a value of 10, because once you do initialize via the pointer, what would happen is p is equal to 10, and so it would just kind of overwrite. All right. L3. Oh yeah, and also memory hierarchy. So latency and bandwidth, like, so there's just different like you get different types of so you have registers, right? And then you have the L1 cache, L3 cache, and then you have all of these other things for your core processor. But they all, they just have different trade-offs between latency and bandwidth that allow you to, do the specific operations. And we'll talk about parallelization later. I see no need to like conflate the memory hierarchy with parallelization, but it is kind of a feature. So state spaces. Now, many scientific disciplines begin by defining a state. That's very important to understand, because computation is not, just some random like exception, right? A particle, you might define a particle as like, I don't know, x and its velocity, right? That would be a jet, technically, a 2 jet. I'm sorry, no, that'd be a 1 jet. If you have a particle and its velocity, that would be like a state. A rigid body would be like you have a radius of something, right? and an angular velocity, and then it's like that's all you need to define a rigid body. And then a field, right? You can define a field, um, you know, as like just some continuous, like technically this would be a space or a field in space. But yeah, with like values at mesh points. So yeah, a state itself, really in each case, we're describing a point in some configuration space that we'll call chi. Okay, chi is a configuration space, and the mathematical structure of this, in the integer n is just the scalar degrees of freedom in the model, and you can just have like a little particle simulator, um, and this would be like consider a second order equation, whatever, right? Do some physics. You don't have to know what this is, but this would be a phase space, and the state of some system, you know, would look something like this, as some function of time, right? As we choose to model it, or in every evolution itself, as we evolve the state, it is a trajectory or discrete sequence. So, it's following some trajectory as we evaluate it through time, and the state itself is kind of, doing its thing, right? It's a damped harmonic oscillator, so you can think about this as like a pendulum, but it's got like a friction in the joints, so it's like kind of like it's dampening, right? And it's slowly just gonna like um, stop moving eventually, right? Now you can think of configuration coordinates by models. So a scalar ordinary differential equation would have dimension 1. Particle itself for some x and v. This would have 6 dimensions because a particle has an xyz coordinate, and then also the rate at which those coordinates are changing. An in-body would look like this for 6 in dimensions, and then a field on the grid would just be the product of the discrete dimensions that we use. All right. So, and as you can see, that would be the state that it finally settles in. Eventually, it's going to settle at 0, 0, 0. Okay. Now, operators. So, once you have a state space that is fixed, states become interesting once we allow them to change. So an operator is going to be defined as a transformation of the state space onto itself. And what that means is like functions, some numerical methods, matrix multiplications, tensors, update rules, compiler passes. They all can be they can all be viewed through this lens of just some operator. Okay, and one application would produce like the n+1th of the operator of the x the nth state, where x again is in our configuration of whatever we're modeling, right? And the distinction between all of these things, like the distinction between like functions and matrix multiplications and update rules, like how it seems to be like they seem to be like not it seems to be smaller than at first appears, if that makes sense. But how what we could possibly do is define, also we can formalize repeated applications. So if you were just to compose operations over and over again, this would be a for loop, right? It's basically a construction of some operation that you're repeatedly evaluating. And then, of course, chaos, periodicity, convergence, all of those things are properties of the operator and how you chose to discretize it. So we could take some, operation here with some parameter r. For r is equal to 3.9, the orbit is going to be chaotic, so there's going to be 2 nearby initial conditions that diverge rapidly. So what you can do is just apply this operator, and you can see like it's got like this kind of chaotic behavior on the logistic map. But it's just it's something that's being computed in the state machine, right? And it's is confined to be on this state, right? Or the configuration space itself is this curve, right? And after iterated composition, you can have like a for loop that would just, this would be like a for loop through the through the logistic map. Technically it's a bifurcation there, but this would be a for loop, just repeatedly applying it over and over after in steps. Okay, so that's a nice intuition. Evolution. So states combined with operators produce evolution. All right. So at this point, you could say like a discrete evolution scheme is an operator such that you devise some scheme that basically tries to solve a continuous or tries to approximate a continuous trajectory, and the error of the scheme will depend on how you choose to discretize it and the smoothness of the function itself that we're interested in approximating that object with. So the connection to scientific computing here actually becomes pretty obvious, because we need to actually use the explicit Euler method or some Verlet or Stromer-Verlet methods. But basically, Euler integration for a simple decay process would be a nice example that I'll show you in a second. But ordinary differential equations, partial differential equations, iterative algorithms, optimization methods, simulation frameworks, they all fit nicely all into this picture. And you can also define the stability as a property of the operator itself, and define fixed points where it's stable only if you have some condition where the discretization has to be less than or has to be less than 2, or for it to converge, right? Now, also another thing that one of my favorite discretization schemes is the for second order systems, you can describe Verlet integration, which is symplectic for Hamiltonian problems. So what it does is, after a long time, it tries to preserve the phase space and volume, so that you could run it for a really long time, and it keeps the computational divergence at a minimum. Where Euler typically, this scheme here is more primitive and it cannot do that. So yeah. So a time step here, as you choose like higher discretization, it just diverges, right? Euler diverges for this is greater than 2. But let's say it equals 1 here. Technically it's stable, it doesn't diverge from the it's probably not a good, it's probably too big of a step, but depends on your preference or whatever problem that you're trying to solve and the level of precision you need. But yeah, this would be like a approximation, and purple would be the Euler, and this is called the Euler orbit. Okay. So yeah, and then here's the Euler. Of course, it completely just went out of phase with cosine. Versus Verlet would stay in phase. Euler kind of like, you can already see it's already diverging a little bit. But yeah, so for systems like this, the Verlet symplectic updates are better. So there's like black magic to this stuff, all right? But that's all I'm saying. But now let's talk about memory geometry. This is a thing that I'm interested in, which is that at some stage one discovers that arithmetic is really, arithmetic itself is not the bottleneck, right? Having to do plus, minus, whatever. Really, it's how we choose to move the memory. And two programs that perform the same floating point operation count can differ in wall clock time by large factors. And the difference is not in the arithmetic, it's in the memory geometry. So, structures embedded into physical addresses, therefore, which cache lines and DRAM pages are touched when the operator runs. That's important because the arrangement of information in memory produces or it influences the performance as strongly as the mathematics would itself. So it influences the performance as strongly as like if you were to mess up a minus or a plus, right? So you can say let's let some topics let's I mean there's several topics that we could get into here. But we can just define the logical data structure of an array of particles or a sparse matrix or tree as a layout embedding that is this injective map. So we're mapping this logical data structure into the address space in im dimensions, we assume, right? Where this is a physical address in A. The geometry of iota determines the spatial and temporal locality when this operator here is spanning the structure. All right. Now, CPUs don't fetch individual bytes from DRAM; they actually fetch cache lines, and this calls upon hierarchy or cache hierarchies and locality. They actually become really important for state machines because, again, I've said this before. You can't simulate a universe, or you can't break the laws of physics in a machine inside of that's in the universe that the laws of physics obey, right? So you have spatial locality, gives you nearby indices that map to different addresses, and temporal locality means the same line reused before eviction. So and also bandwidth, latency, they also become important because of how the core processors are structured. But we can demonstrate this actually. So let's compare something called an array of structures, where each particle stores contiguously, as if you just say struct particle and then float them, versus structive arrays and then coordinates of the same type are contiguous, where you just float them as arrays. If you sum all of x of I, every particle in an array of structs, but strides across unrelated, x, y, y, z fields, loading cache lines that are actually only partly, you're going to only load cache lines that are only partly used. And the reason why is because of their space-like separated. This comes from relativity. I'm not pulling this out of my ass. This is why the machine is very important to this would be a good moment to introduce relativity to a computer science person, I think, is understanding the actual state machine themselves. But anyways, and structure of arrays, you can load lines with useful x sub I values, and the operation itself, or the operation count, is identical, and the bytes that are moved are not. So here would be like an array of structs, how you choose to, sit each struct inside of this and straddle the cache lines. And then, cache lines such 3. And then here you can have all contiguous, so fewer cache lines that sum to x, right? Now, of course, in practice, it's not this perfect. So you'll get clipping. But for structive arrays, you get this. It's just different ways to organize memory, if you will, right? And they have different techniques, if you will, for playing around with the core processor. Roofline bound. So if pflop is the peak arithmetic throughput, then and b is the memory bandwidth, then you also get a lower bound on the you get the roof. This is called the roofline bound, but basically when the byte term dominates, you'll rearrange the data layout. That'll matter much more than shaving operations. All right. Now we can also talk about parallelism. So nature typically likes to have parallel systems because that's just how nature is, study physics. But modern hardware will attempt to exploit that fact here. So multi-core CPUs and GPUs can be viewed as systems that are really just capable of applying many operators simultaneously. And so, parallel computation applies operators to, subspaces of the configuration space. And with synchronization, with two subspaces that overlapped and shared memory or halo and grid codes, locks on LAS data. With the LAS data, the global evolution is coherent only if these interfaces are handled consistently. So, also Amdahl's law. So if you suppose a fraction of work parallelizes perfectly across n cores, then the remaining fraction, 1 minus p, must run serially. And Amdahl's law gives you a speed up function that as n goes to infinity, it approaches 1 over 1 minus p. And so we can kind of visualize that. And it looks like this, where we basically can compare the single-threaded and parallel implementations from some simple some simple vector optimization here that we're doing, and that's what's happening. So the speed up here, as you can tell, as p gets like really high, you get good speed up, but like around p is like much smaller. You're limited asymptotically as to how much you can actually speed them up, even if you have a bunch of cores. So parallelism is a super important concept. All right. Now, hold on, my computer's kind of getting low. You know what I'm saying? But yeah. So, anyways, parallelism. Basically, you just coordinate the evolution of a system in a distributed state over subspaces of your configuration space. Yeah. And then of course total time, which would have a lower bound of the computation and the time of between the cores, between the bandwidth and the link bandwidth, and I think this is minimizing just the regular bandwidth. Oh, the bandwidth as a function, right? False sharing occurs when two cores write different variables. So you just kind of like these would be things that make this total time bound or moving bytes. Sorry, not bandwidth. These would be variables that like make this time floor, this communication as a time floor equation. Not greater than or equal to. Okay. So there's other things that are there, but yeah, communication time. Good decomposition keeps the number of bytes small. So just use less memory. Yeah. So programming languages. We've gone this far talking about computation, and we're at like chapter, I guess, or section 9, and I'm barely talking about programming languages. So only now are we allowing programming languages to enter the discussion, because and the reason for delaying them is because languages, I mean, it's just simple. Languages are just representations. That's all they are. Languages themselves are not computation. They're not the underlying object. So you can express the same operator in C, C++, Rust, Julia, Python, whatever other language. Doesn't matter, because like the syntax changes, but the operator itself is what remains. And how whatever the operator still is the operator that it's representing. All right. So I'm just showing you, like, here's C. This is what it would look like in C. For an Euler step, this is what it would look like in C++. This is what it would look like in Rust. This is what it would look like in Python or Julia. All right, so it's pretty, I mean, of course, there are different representations and they have different goals, right? So Python is like, C is like all about addresses and raw bytes and explicit operators, right? Like you gotta know all of those things and the values that those addresses evaluate to. But manual, and of course you have to, basically the constraint is that you have to understand how to have memory safety, because I mean memory itself is like the core. I guess paintbrush, if you will, that C plus or that's people with C that use C or C plus plus type languages are constantly, thinking about. Now, Rust is more about ownership and borrowing of memory regions because that's just the crypto language, right? um, it's all about topologically guarding some state space in your machine and like shielding it and owning it. So no data races at compile time uh, when safe, right? That's like the static constraint. Python, just high level semantics, right? That's all the programmer really learns from Python, and it hides really this mapping, um, and it pays interpreter and allocation costs. So it pays interpreter and allocation costs to hide the im map, right? And let's remind ourselves of what im is. Im is memory, and why do we care about memory? Because it hides everything that C++ tries to C++ is very concerned with controlling, which is the address space and the value space. And then Python's like, we don't care about addresses and values, we just care about semantics, right? So that comes with research. A lot of research level things are built for Python. So scientific architectures. Well, basically, I mean, before we move on, I think a statement could be made that programming languages are just coordinate systems on a space of computing or on the space of computations. So we can compute the same exact thing, but we have different coordinate systems to compute the exact same thing abstractly. So that's just a that would be, I guess, a true statement. I don't know how convincing that explanation was, but yeah. Finally, by this last stage here, you can think of, you can see the recurring pattern, which is that across, viewing computation as some geometric thing or numerical simulation, if you get into finite elements or computational physics, machine learning, other domains, the same structural kind of thing will appear, which is state, operator, memory, evolution. And the details on how you do that is different. That's basically how we choose to answer, this 4-question thing when we're building a scientific architecture. And I count finance or quant finance as a financial science or as a type of science, or a data science, if you will. So, you know, you can click rows here. Memory itself. We have like a little cheat sheet here for PDEs. So if you have a PDE, you would represent them with arrays and evolve them with time step stencils, whatever, that are compatible with, the fact that the universe has the speed of light. You don't want to make a grid that violates the speed of light with or whatever stencils or locality. Uh, Geometry itself, manifold, simplicial complexes. How they would represent them is with sparse and stiffness, and solve them. That's how you would evolve them, just by solving their I guess like Poisson type equations. Or oh no, this would just be linear sparse stiffness. And then alpha engines for like finance. You would have some stochastic state. That's the object. Market feed data, feature buffers, and then that's how you would evolve it. So yeah, this is just how to generally think about it. Scientific software is just engineering of information bearing systems that evolve with time. So just to close everything, again, these notes and my ranting, this isn't to replace your conventional computer science like idea of everything. And I'm not trying to argue like that there's a single correct way to think about computation, but I just want you to think. I mean, the purpose of all this is pretty modest. It's just to the hope that simply that viewing machines, information, memory, operators, numerical evolution, all of these things through some common like lens in physics may reveal some connections that are um, not just physics but also like the mathematics of machines. These things are often really obscured by disciplinary boundaries. So with programming languages and high performance software, these aren't really isolated topics in my opinion, but they're just like different realizations of some common structure. So you know, maybe one possible way to summarize that structure um, would just be, machines, information, memory, the states, operator, and then just like how they evolve. And then, of course, there's these extra type of things that typically are reserved for more like advanced type classes. But I mean, I think they're important enough to mention. All right. So thank you for watching, and I'll see you guys next time.